My sincere greeting to one and all. I am Tamanna from Basic Chemistry Junior Second Year. Today I am here with chapter Phenols. Introduction. Phenols are aromatic hydroxy compounds in which the hydroxyl group is directly attached to an aromatic ring. They are may be represented by general formula AROH, where AR represents a phenyl, a substituted phenyl, or some other aryl group such as naphthalene. Depending upon the number of hydroxy groups attached to the aromatic ring, the phenol may be classified as mono, di, trihydric phenols, and so on. For example, we have phenol monohydric, O cyrosol monohydric, arsenicol dihydric, pyrogalol trihydrid. The hydroxyl group attached to the aromatic ring is known as phenolic groups. As we know what phenols are different from aromatic hydroxy compounds in which the hydroxy group is present in the side chain. The latter type of compounds are in fact aryl substituted aliphatic alcohols and their behavior is similar to that of aliphatic alcohols. However, both phenyl and aromatic alcohols resemble each other in undergoing the electrophilic aromatic substitution and in certain other respects. Nomenclature of phenols. The simplest member of phenol is always known, but its popular name is phenol, although its IUPAC name is benzoyl. All subsequent monohydric phenols are named as derivative of phenol, but methyl phenols possess special common names. The position of substituents with respect to the OH group are denoted by ortho, meta, and para in common system, but by number in the IUPAC system with OH group carrying the number 1. The following example illustrate the method of naming phenols. The name given in brackets are common names: phenol, 2-chlorophenol, orthochlorophenol, 2,4-dinitrophenol, 2-methylphenol, 3-methylphenol, 4-methylphenol, orthomethylphenol, metaphenylnitol, paracrysols. They are their common names. The di or trihydric phenols have the IUPAC names benzene-diols and benzene nitriles respectively, but most of them are known by their special name as given below: 1,2-benzene-diol or 1,2-dihydroxybenzene catechol, 1,2-benzene-diol, 1,3-dihydroxybenzene, 1,4-benzene-diol or 1,4-dihydroxybenzene, hydraquinone or quinol, 1,2,3-benzene-nitrol or 1,2,3-trihydroxybenzene, 1,2,3,5-benzene-nitrol or 1,3,5-trihydroxybenzene. It should be noted, however, that when a compound contains some functional group such as carboxylic acid, ester, or carbonyl group in addition to phenolic group, the compound is named as hydroxy derivative of the acid, ester, or carbyl compound. For example, 4-hydroxybenzaldehyde, 2,4-dihydroxybenzoic acid, ethyl 4-hydroxybenzoate. Phenyls structure and bonding. Phenyls are compounds having the hydroxyl group directly bonded to the benzene ring, while the oxygen of hydrogen group is in sp3 hybridized state. The carbon of benzene ring to which oxygen is bonded is in sp2 hybridization state. Resonance interactions take place between a lone pair of electron on oxygen and the benzene ring so that phenol exists at resonance. Hybrids of resonating structures are shown below. Due to the resonance, the carbon-oxygen bond acquires some double bond character and becomes shorter and stronger than the carbon-oxygen bond in alcohols. As a result, phenol do not undergo substitution reaction of a OH group like alcohols. At the same time, oxygen acquires a slight positive charge due to which it attracts the electron pair of OH bond strongly towards itself. As a result, the OH bond in phenol becomes more polar than in alcohol. Due to above structural features, phenol behave differently from alcohol in many respects and are treated as a separate class of compounds. Method of formation. The compound employed generally method of preparation of phenol are described below. First, hydrolysis of diazomium salt. This is probably the most convenient method of preparing phenols. The reaction is usually carried out by slowly adding diazomium salt solution to excess of boiling dilute sulfuric acid. For example, benzene diazomium chloride plus H2O in presence of H positive plus heat gives phenol plus HCl plus N2. Since hydrolysis is carried out under very mild conditions, other groups in molecule of diazonium salts are not affected. Meta-nitrobenzene diazomium hydrogen sulfate presence of H positive ion heat gives meta-nitrophenol. Second, from isopropyl benzene cumene. This method is used particularly for the large-scale preparation of phenols from isopropyl benzene, popularly known as cumene. Cumene is readily oxidized by air to form cumene hydroperoxide, which is converted into phenol and acetone by treatment with an aqueous acid. Cumene in the presence of 303 to 353 Kelvin temperature gives cumene hydroperoxide, then H3O positive gives phenol and acetone. Mechanism. The mechanism of conversion of cumene hydroperoxide into phenol gives a series of 5 steps as shown below. In step 1, peroxide get converted into a protonated peroxide from which a water molecule is eliminated. Step 2, to form an intermediate having electron deficient oxygen. In step 3, a 1 to 6/5 of phenyl group take place, giving a carbocation which is resonance hybrid of two structures. The carbocation takes up a molecule of water. Step 4, to form a hemiacetal. The hemiacetal finally breaks. Step 5, to yield phenol and acetone. It may be noted that cumene itself is obtained by a Friedel-Crafts reaction between benzene and propylene in presence of uric chloride, obtained by fusion of sodium salt of aromatic sulfonic acid with sodium hydroxide followed by acidification. For example, sodium toluene sulfonate into paracetisol. Only the first two methods are included in syllabus. This method cannot be applied to salts of sulfonic acid containing substituents such as ClNO2COOH due to the possibility of various side reactions. Fourth, from aryl halides. Substituents phenol having electron withdrawing group like NO2 group in orthopara position to the OH group can be easily prepared from the compressed corresponding aryl halide by treatment with aqueous sodium hydroxide. Phenol itself is also manufactured by this method by heating chlorobenzene with 10% sodium hydroxide solution at 603 to 623 Kelvin under a pressure of 200 atmosphere in presence of copper salt. The process is known as Dawes process. Fifth, from phenolic acid. Distillation of sodium salt or phenolic acid with soda lime yield phenols. For example, soda silicate gives phenol plus Na2CO3. Sixth, from Grignard reagent. Phenol may be prepared by treatment aniline magnesium bromide with oxygen followed by hydrolysis of the product. Seventh, from coal tar. Phenols and cereals are obtained on a large scale from the middle oil fraction obtained on distillation of coal tar. Physical properties. First, physical state. Phenol are generally colorless liquid or solid, but they are usually appear slightly colored as they readily get oxidized even in air, and the oxidation product are colored compound at the same time. Substitution like NO2 also impart color to phenol. Second, boiling point. Due to the formation of intermolecular hydrogen bonding, phenols oil considerably larger, higher than corresponding hydrocarbons and aryl halides which do not contain hydrogen bond. For example, phenol molecular weight 94 boils at 455 Kelvin, while toluene molecular weight 92 boils at 384 Kelvin only. Third, solubility. Phenols are practically insoluble in water, although phenol itself is, and some di and trihydric phenols are fairly soluble. The solubility of these compounds is probably due to the formation of hydrogen bonds with water, but the extent of hydrogen bond formation is very small due to large size of phenyl group, which makes the polar character of OH group. All phenols are soluble in aqueous alkaline solutions due to the formation of water-soluble salts. Phenols containing substituents such as NO2 can also form intramolecular hydrogen bonding. This is responsible for certain interesting observations. For example, orthonitrophenol has a lower boiling point and smaller solubility in water than meta or para isomer. This is because the ortho isomer forms intramolecular hydrogen bond between the oxygen of nitro group and the hydrogen of hydroxyl group. The phenomena is also known as chylation, Greek word chylekla, due to the intramolecular hydrogen bonding or chylation. The orthoisomer has only very small tendency to form intermolecular hydrogen bonding. On the other hand, in meta and para isomer, the hydroxyl and nitro groups are substituted. Then intramolecular hydrogen bonding is not possible without intermolecular hydrogen bonding takes. As a result, meta and para nitrophenols have higher boiling point and are soluble in water. Chemical properties. Phenols are highly reactive compounds which combine the reaction of both the hydroxyl group or aromatic ring. The important reaction of phenol are discussed below. First, reaction of phenolic groups. Acidity. Phenols are weakly acidic compounds. They react with aqueous alkali metal hydroxide to form salts known as phenoxides. Phenol gives sodium phenoxide with NaOH plus water. However, phenols do not react with aqueous carbonates or bicarbonates. Moreover, the salt of phenols are converted into phenols by aqueous mineral acid, carboxylic acids, or even carbonic acids. These observations indicate that phenols are very weak acids, weaker than carboxylic acids or even carbonic acid. This is confirmed by a comparison of their acidity constant Ka or pKa values. While phenols have Ka value of the order 1 into 10 raised to power minus 10, carboxylic acid and carbonic acids have Ka value of about 1 raised to power 10 raised to power minus 5 and 10 raised to power minus 7 respectively. And these days, acidic strength are usually represented in terms of pKa value, which is the negative logarithm of acidity constant, that is pKa is equal to minus log Ka. For example, pKa of phenol Ka is equal to 1.3 into 10 raised to minus 7 is 9.8. It may be noted that a stronger acid have larger Ka value but smaller pK value, while a weaker acid has smaller Ka value but larger pK value. Even though very weakly acid themselves, phenols are much more acidic than phenols, which have pKa value of order 1 into 10 raised to power minus 16 to 1 raised to power 1 into 10 raised to power minus 18. This appears to be rather surprising, since both phenol and alcohols are characterized by the presence of hydroxyl group, but then the reason of that an OH attached to an aromatic ring is so much more acidic than a OH attached to an alkyl group. We should attempt to answer this question by considering the stability of the ions formed relatively to the substability of an ionized compound. Explanation of acidic character. The ionization of phenol is an equilibrium reaction involving the unionized phenol and phenoxide and hydronium ions. For example, now neither a phenol nor phenoxide ion can be represented by only one valence bond formula. On the other hand, each of these them is a resin hybrid of various contributing structures as shown below. It may be noted that the contributing structures IC 1C, 1D and 1E of phenol involves separation of charge and are therefore less stable than the structure of first A and first B. On the other hand, in case of phenoxide ion, none of the contributing structure involves charge separation and the structure are almost equally stable. As such, phenoxide ions are resonance stabilized to a greater extent than phenol. Therefore, the equilibrium between phenol and phenoxide ion favors the formation of phenoxide ion and hydronium ion, that is, phenol moderate resonance stabilization plus H2O in equilibrium gives phenoxide ion large resonance stabilization. This accounts for the acidic character of phenols. Comparison with alcohol. In case of alcohol, the equilibrium reaction involves alcohol and alkoxide ion do not favor the formation of alkoxide ion and hydronium ion. This is because there is no resonance stabilization of alkoxide ion relative to alcohol, since neither the alcohol nor the alkoxide ion exhibit resonance, that is, alcohol no resonance stabilization, alkoxide ion no resonance stabilization. Hence, it should be surprising that compared to alcohol, phenol ions more readily to form phenoxide ion and hydronium ion. In other words, phenol are more acidic than alcohols. Effect of substituent on the acidity of phenols. The acidity of phenol is strongly influenced by substituent attached to the benzene ring and their position. This is because the state of equilibrium in the reaction between phenol and water to furnish phenoxide ion and the hydronium ion is independent upon the stability of the products relative to the stability of the reactant. Any factor which stabilizes the phenoxide ion more than the parent phenol should increase the acidity, while any factor that destabilizes the phenoxide ion should decrease the acidity of it, illustrated below. First, nature of substituent on the benzene ring. A electron withdrawing substituent. Phenol having electron withdrawing substituent such as halogen and nitro group are more acidic than phenol itself. This is because an electron withdrawing substituent group say G attracts the electron toward itself and thus disperses the negative charge on the phenoxide ion. As a result, it stabilizes the phenoxide ion and increases the acidity of phenol. Electron withdrawing groups such as NO2, Cl, COH, G attract electron toward itself, disperse the negative charge of an ion and thus stabilizes it. B. Electron releasing substituents. Phenol containing electron releasing groups such as alkyl groups are less acidic than phenol itself. This is because an electron releasing substituent say G releases the electrons away from itself and thus intensify the negative charge on the phenoxide ion. In this way, it destabilizes the ion and therefore by decrease the acidity of phenols. In short, electron withdrawing groups increase the acidity of phenol while electron releasing group decreases the acidity of phenol. F table 5.1 shows the effect of different substituent on the acidity of phenol. Second, position of substituent relative to hydroxide group. Apart from nature of the substituent, the position of the substituent relative to hydroxyl group also have large influence on the acidity of phenol. This may be explained as follows. First, the stabilizing or destabilizing influence of the substituent operate through inductive effect as well as resonance. The intensity of inductive effect of the substituent decreases as its distance from the OH group increases, that is ortho position, meta position, para position. First, ortho position is more than meta than para. That is why the acidity of cyclophenol is in order. Ortho cyclophenol is more acidic than cyclophenol than chlorophenol than paracyclophenol. So third, the resonance effect is more pronounced if the substituent is in ortho or para position than in meta position. To understand this, let us examine the contributing structure of ortho, meta, and para nitrophenol phenoxide ions. These are the resonating structures of orthonitrophenol ions, para-nitrophenol ions, and meta-nitrophenol ions. It may be seen that each of the ortho-para-nitrophenol ion is a resonance hybrid of 5 contributing structures in one of the structure. In case the structure marked conjugation is extended up to oxygen to atom of the nitrogen group, but not such conjugation is possible for meta-phenoxide ion, and it has only 4 contributing structures. The net result is that there is greater resonance stabilization of ortho and para anions and then the meta and isomers such as ortho or para meta nitrophenols are much stronger acid than meta-nitrophenol as shown in table 5.1. An interesting observation is that certain phenols having electron withdrawing groups in the ortho position are weaker than para isomers. For example, orthofluorophenol is a weaker acid than parafluorophenol, or orthonitrophenol is a weaker acid than para-nitrophenol. This can be attributed to the formation of intramolecular hydrogen bonding in case of orthoisomers as shown below. Second, ether formation, Williamson synthesis. On reaction with alkyl halide or dialkyl sulfate in alkyne medium, phenol are converted into corresponding alkyl ethers. The allyl halide or sulfate undergo nucleophilic substitution by the phenoxide ion present in alkaline solution of phenol. Reaction between sodium or potassium phenoxide and allyl bromide led to the formation of allyl ether. Clemmensen rearrangement. This is an interesting rearrangement reaction involving allyl ethers. When heated at 475 Kelvin, the allyl group of the ether migrate from ether oxygen to the ring carbon at ortho position. For example, allyl phenyl ethers to ortho allyl phenol in presence of 475 Kelvin temperature. If both the ortho and para position are already occupied, the allyl group migrate to para position. For examples, allyl 2,6-dimethyl phenyl ether to 4-allyl 2,6-dimethyl phenol. Mechanism of ortho rearrangement. Isomerization involves a concurrent mechanism in which the cleavage of allyl oxygen bond is synchronized with the formation of allyl carbon bond to the ortho position. The cyclohexane dienone intermediate thus formed undergo a tautomeric chains to give the orthoallyl phenol, in which the ring regains the aromatic characters as depicted below. It may be carefully noted that it is the beta. May be carefully noted that it is the gamma carbon of the alkyl group with respect to oxygen which attaches itself to the ring carbon. This is supported by the fact that orthomigration involves an inversion in the position of substituent in alkyl group with respect to that of starting compound. For example, given below. Mechanism of para-enrichment. Para-isomerization involves two stages. In the first stage, orthomigration takes place and the cyclohexadienone intermediate is formed, but this intermediate cannot undergo tautomerization since there is no hydrogen at the ortho position, as both these positions are already substituted. As such, these intermediate undergo another migration of alkyl group to ultimately yield the final product. It may be noted that in para-isomerization, two migrating take place, each of which is accompanied by inversion. In other words, one inversion is followed by another inversion, so that there is no net inversion in the position of the substituents with respect to the starting compound. For example, given below. Third, ester formation, acylation. Like alcohols, phenols are converted into esters by reaction with carboxylic acid, acid chlorides, and anhydrides. However, in actual practice, esterification is better carried out by the use of acid chlorides or anhydride rather than acid themselves. Ferris rearrangement. If an ester of a phenol is heated with aluminium chloride, the acyl group migrate from the phenolic group oxygen to the ortho or para position on the ring. This is called Ferris rearrangement. For example, phenyl propionate in presence of AlCl3 413 to 4250 kelvins, para hydroxyphenyl ether ketone or orthohydroxyl phenol ether ketone. At low temperature, para product predominates, while at high temperature, orthoisomers is main product. Mechanism. The rearrangement probably involves the formation of an acrolein ion RCO positive, which then attract the aromatic ring, as in Friedel-Crafts acylation ITI. The complete mechanism may be summed up as follows in the steps of ortho attack, para attack. Fourth, reaction with zinc dust. When distilled with zinc dust, phenol are corresponding hydrocarbons. For example, phenol plus zinc in presence of heat gives benzene plus ZNO. Fifth, reaction with ammonia. When heated with ammonia at high temperature and pressure in presence of catalyst like anhydrous zinc chloride, OH group of phenols is replaced by NH2 group. For example, phenol plus NH2 anhydride ZnCl gives phenol anisole plus H2O. Reaction of aromatic ring, electrophilic substitution. Phenol readily undergo electrophilic aromatic substitution reactions. The OH group linked to an aromatic ring activates the ring to the electrophilic substitution and direct the incoming group to ortho and para position. In fact, the OH group is very powerful activator, and unless precautions are taken, Polish substitution takes place. Explanation of ortho-para directing and activating influence of OH group toward electrophilic substitution. The OH-para directing and activating influence of OH group toward electrophilic aromatic substitution can be explained in terms of assumptions that oxygen of these groups can share more than one pair of electrons with the ring due to the resonance. While phenol undergo electrophilic substitution, the contributing structure of the intermediate Carbocations formed by the attack of electrophiles say E positive at ortho, para, and meta position are as shown below. Ortho attack is most stable, para most stable, and meta attack. The carbocation formed by ortho attack is resonance hybrid of four structures third A and third D. Of these four structures, the structure third D is particularly stable since in it each atom except hydrogen of course has a complete octet of electrons. Similarly, in para attack, the carbocation is a resonance hybrid of four structures fourth A to fourth D, of which fourth D is the most stable, but in case of meta attack, the carbocation is a hybrid of only three structures fifth A to fifth C, where there is no structure corresponding to third D and fourth D. This means that the positive charge of the ortho and para ions are dispersed over more atoms than is that of meta ion. It is therefore apparent that the hybrid carbocation resulting from ortho and para attack are more stable than the carbocation resulting from the meta attack or from the attack on benzene itself. The substituent in phenols occurs mostly at ortho and para position and occur to the fast rate than in case of benzene. The important electrophilic substitution reactions of phenol are discussed below. Sixth, halogenation. On treatment with halogen, phenols are very rapidly halogenated, forming polyhalogens derivative. For example, reaction of phenol with an aqueous solution of bromine immediately produce a precipitate of tribromophenol. In fact, the reactivity of phenol toward halogenation is so great that even substituent like SO3H group is present in if present in ortho or para position get displaced. For example, phenol sulfonic acid to 2,4,6 tribromophenol. Halogenation can, however, be limited to monohalogenation stage by performing it at a low temperature and is a non-polar solvent such as carbon tetrachloride or carbon disulfuric. For example, phenol plus Br2 in presence of CS2 273 Kelvin gives para-bromophenol plus ortho-bromophenol plus HBr. The above observation can be explained in terms of the fact that greater the electron density around benzene ring, the more stable it can undergo electrophilic substitution reaction. In aqueous solution, phenol ions to form phenoxide ion due to the presence of negative charge on it. Oxygen to the phenoxide ion can release electron toward the benzene ring to a large extent. As a result, electron density around benzene ring becomes very large, so that the ring is highly activated and undergoes tri-substitution. In non-polar solvents such as CS2, phenol does not undergo ionization to an appreciable extent and occur mainly as unionized molecules. The OH group of phenol can release electron toward benzene ring only to a small extent. As a result, benzene ring is not strongly activated, and therefore it undergoes only monosubstitution reaction. Seventh, nitration. Nitration of phenol gives poor yield of the expected nitro compound. This is because phenol are easily oxidized, and nitric acid can bring about not only nitration but also oxidation in starting phenol. For example, use of concentrated nitric acid in the above reaction lead to the formation of 2,4,6 trinitrophenol or picric acid in low yield. 8th, sulfonation. Sulfonation of phenol proceeds readily to yield ether, either ortho or the para isomer as the main product depending upon the temperature of the reaction. In general, low temperature favors the formation of ortho isomers while high temperature favors the para isomer. On heating to 373 Kelvin, ortho phenol sulfonic acid changes to the thermodynamically more stable paraphenol sulfonic acid. Ninth, Friedel-Crafts alkylation. Phenol undergo Friedel-Crafts alkylation, forming predominantly para-isomers. The reaction is carried in presence of HF. Normally, Friedel-Crafts reaction is carried out in presence of anhydrous AlCl3 but in case of phenol this catalyst is not used. This is because electron deficient Al atom of AlCl3 coordinates with a lone pair of electron on the oxygen of OH group to form a complex. This suppresses the activating influence of OH group so that the yield of the product is very poor. 10th, Friedel-Crafts acylation. Phenol can also undergo Friedel-Crafts acylation to form ortho and para hydroxy ketones by treatment with acid chlorides and acid anhydrides, but the hydroxide ketones are generally prepared by Ferri's rearrangement. 11th, Gutterman synthesis. When treated with mixture of hydrogen cyanide and hydrogen chloride in presence of anhydrous aluminum chloride, phenol give phenolic aldehydes. The reaction is known as Gutterman synthesis, constituent an important method for synthesizing phenolic aldehyde. For example, given the aldehyde group gets attached to preferably to para position. Mechanism. Gutterman synthesis is an electrophilic aromatic substitution in which the attacking reagent is formaldinium ion formed from HCN and HCl in presence of anhydrous AlCl3. The complete mechanism may be summed up as follows. HC triple bond N plus HCl gives to HCCl double bond NH and the 12th, Husband-Hose reaction. This is an acylation reaction of polyhydric phenol having hydroxyl group in meta position which each other. It is carried out by treating such phenols with alkyl cyanide and hydrogen chloride in the presence of anhydrous zinc chloride or aluminum chloride followed by hydrolysis. For example, the formation of 2,4,6 trihydric acetophenone. Mechanism. The mechanism of the reaction is similar to that of Gutterman's reaction and is summed up as given below. Special reactions of phenols. 13th, coupling with diazonium salts. When treated with diazonium salts in weakly alkyl solution pH 9 to 10, phenol undergo coupling to the formation hydroxo compounds for benzene diazonium chloride plus phenol give in presence of weakly alkyne gives parahydroxobenzene plus HCl. Kolbe's reaction, also known as Kolbe-Schmidt reaction, carboxylation. When heated with carbon dioxide under pressure, sodium salt of phenol undergo carboxylation to form salt of phenolic acid, the orthoisomers being the main product. For example, when sodium phenoxide is heated with carbon dioxide under pressure, sodium salicylate is obtained as the major product. Sodium phenoxide plus CO2 in presence of 398 Kelvin to 1 temperature and 1 to 7 atmospheric pressure gives sodium salicylate main product, and in presence of H positive gives salicylic acid. Mechanism. The mechanism Kolbe's reaction is believed to involve the electrophilic attack by carbon dioxide on phenoxide ion as shown below. Riemann-Tiemann reaction. On heating with chloroform and alkyl phenol are converted into phenolic aldehydes, an aldehyde group being introduced on the aromatic ring, generally in orthopara to the OH group. For example, when phenol is heated with chloroform and aqueous sodium hydroxide, salicylic is obtained as the main product along with a small amount of para isomer salicylic aldehyde as main product. when reaction takes place between phenol plus CH3Cl CHCl3 plus 3 moles of NaOH in 333 to 343 Kelvin temperatures gives salicylic aldehyde main product plus 3 moles of NaCl plus 2H2O. Mechanism. The mechanism of reaction involves the electrophilic substitution of phenoxide ion formation of in solution by the action of alkyl on phenol. The attacking nucleophilic reagents is the electrodeficient dichloromethyl CCl2A carbene generated by the action of alkali on chloroform. Dichloromethylene is electrically neutral, but it acts as an electrophilic reagent as the carbon atom present in it is surrounded by only 6 valence electrons. The complete mechanism may be summed up as follows. If carbon tetrachloride is used in place of chloroform in Riemann-Tiemann reaction, phenol gives rise to phenolic acid. Phenol plus CCl4 plus 4NaOH gives, followed by acidifications, gives salicylic acid, orthosalicylic acid and parasalicylic acid plus 4NaCl plus H2O. Lederman's reaction is 16th one. Phenol undergo condensation with aldehyde in presence of an acid or a base as a catalyst. The product initially formed get polymerized to form commercially important polymers. For instance, when phenol is treated with formaldehyde in presence of an acid or alkali, a mixture of ortho and para hydroxybenzyl alcohol is formed. Phenol plus formaldehyde gives hydroxyl benzene alcohol. The alcohols formed undergo polymerization to form a resinous polymer called bakelite. Mechanism of initial condensation. The initial reaction between phenol and formaldehyde involves the electrophilic attack by formaldehyde on phenoxide ion, alkaline medium, or protonated formaldehyde on phenol. Acidic medium are summed up as acid catalyzed protonated formaldehyde, base catalyzed 16th phenethylene reaction. On reaction with phthalic anhydride in presence of concentrated sulfuric acid or anhydrous zinc chloride, phenol are converted into phenethylenes. For example, phenols forms phenolphthalenes as shown below. Phenol plus phenol in presence of H2SO4 gives phenolphthalein plus H2O. Phenolphthalein is used as an indicator in acid-alkaline titration. It is colorless in acidic medium but changes to pink color in alkaline medium. 18th reaction with ferric chloride. Phenol gives a violet coloration with ferric chloride due to the formation of water-soluble complexes ferric phenoxide C6H5O all 3 Fe. Other phenols also form colored complexes green, blue, violet, or red. On treatment with ferric chloride, the reaction is used as an important test in the identification of phenol. This test is not given by alcohols. The last reaction is Lieberman's reaction. On treatment with sodium nitrate dissolved in concentrated acidic sulfuric acid, phenol gives a red color. The color changes to blue on addition of aqueous sodium hydroxide. The reaction is known as Lieberman's reaction. So, thank you.